I'll continue working on this example that's been very useful to us in understanding dynamical 3-disc pinball or 3-disc billiard. And it's very useful in understanding discrete symmetries because this is the first example where you have a non-abelian group, meaning its matrix representation have matrices which multiplication depends on the order in which you multiply the matrices. So it's non-abelian. The first examples I gave you were all abelian examples, so they're easy. And I'll do part of this, and then Oliver will do another part of this. And once we are done, we'll understand about irreducible representations, and that's really key. So now remember, just studying how evolution works on state space, we came to this thing that I call regular representation. Now I'll work it in detail for 3-disc problem or triangle problem. So let's say that we have 3 disks in a plane. And I'll label them anti-clockwise 1, 2, 3. Not important at all. And then I observe that there are 3 symmetry axes for this arrangement of equidistant equal radius disks. And what happens with the symmetry axis is that if I flip the whole image, the image goes into itself by label exchange. So for example, if I flip in this direction, which I'll call sigma 1, 2, then disk 1 becomes disk 2 becomes disk 1, but disk 3 remains a disk 3. And similarly, I can flip 2, 3. And 1, 3. So there are 3 reflection operations. But then I can also take all 3 disks and rotate everything by what I'll call C 1/3. 1/3 of the full circle, and then 1 becomes 2, 2 becomes 3, and 3 becomes 1. And if I repeat this operation, and I rotate by C 2/3. So this is a group that has many names, but let's call it a Hidel group of 3 elements. And its elements identity, 3 reflections, sigma 1, 2, sigma 1, 3, sigma 2, 3, and 2 rotations by 1/3 of the full circle and 2/3. Now that's what I mean geometrically in this particular problem. But there are other notations which are more useful for this finite group, which are less tedious. So let me relabel these things and give them names which will be more convenient in what follows. So let's call them identity A, B, C, D, and F. This is sigma 1, 2, 3 in my particular notation. This is B, and this is that. And this is rotation by 1/3 circle, and this is rotation by 2/3. And this is just to be correct, but it doesn't really matter. The only thing that matters is there is one identity, there are 3 flips, and there are 2 rotations. But the way I'm doing it, I'm being very explicit. And now I can write these things in a different notation, which is often convenient. I'll write them in permutation notation. So I'll call identity, I'll call it I start with 1, 2, 3, and after I've done my thing, they're still in the same order. Then I start with 1, 2, 3. I don't touch 1, but exchange 2 and 3. I call B 1, 2, 3. I don't mess with 2, but exchange 3 and 1. Then I don't mess with third disk, but I interchange the first 2. Now these, I start with 1, 2, 3, I move 1 to 2, I move 2 to 3, I move 3 to initial position. And for F, I do it in the other order, 2, 3. So I move 2 here, I move 3 there, I move 1. So I rotate them the other order. And it was already understood in 19th century that it's easier to think of these things just by drawing pictures. So if you draw just 3 lines here, and you imagine you had 3 disks with labels on them, then this operation doesn't change them. This operation doesn't change the first one, but exchanges these 2. This operation doesn't change this one, but exchanges first and third. This operation exchanges 1 and 2, but doesn't exchange 3. This operation sends 1 to the right, sends 2 to the right, sends 3 by cyclic symmetry to the beginning. And this one sends 2 to the left, 3 to the left, and 1 in the other direction. And it's easier to understand what these things are by picture. You'll see when I do multiplications. So now what we need to know is what happens if you apply successive operations. So one thing that's very obvious is that if I exchange 2 and exchange them again, I'll come back. So it's quite clear that we will have a square equals identity. Same for the other flip, flip twice, identity, flip twice is identity. Now if I rotate 2 times by 1 notch, I end up here. So, I obviously have the d square equals f. And if I go 2 notches in the other direction, it's just like going 1 notch in the original direction, so I have this. But then I have to also compute what happens if I first flip and then rotate, etc. And this notation is very convenient, so I'll just do 1 calculations for you. So I'll show you that if I first take operation D and then operation A, I'll show you the same thing as just applying operation D, which is a flip. So you first rotate, and then flip, and that's same as another flip. So how do you show this? You can write it in permutation notation. So in permutation notation, this is 1, 2, 3, 1, 3, 2, 1, 2, 3, 3, 1, 2. But in this diagrammatic notation, it's really simple. What I do is I first apply this operation, which was 1, going from the top. This operation, then I apply this operation. This operation looks like that. And I just connect them. And I look at the result. And I find that this element stays where it used to be, but this one and this one gets exchanged. I look at my table, and that's actually element B. So this is a simple permutation representation of the symmetry representations. So this enables you now to fill out the multiplication table of all possible forms. So let me write the multiplication table. Once I've written multiplication table, I've defined abstractly a finite group. So what we'll find convenient is to write multiplication table in the following format. You'll write identity A, B, C, D, F. But here, and that's because what we already did, we realized that we actually care about the inverse operation. It's convenient to write inverse of A, inverse of B, inverse of C, D, and F. And as every group element has unique and inverse, this is same multiplication table. They've just been permuted in some order. And then you start filling it out. So on diagonal, in this format, on diagonal, I just get identity because I'm multiplying everybody by its inverse. And then I'll fill out the table here. So multiplying something by identity just reproduces what we just saw. So these are trivial. Row and column A, B, C, D, F. Same here. But now I'll write out the inverses. So inverse of A is A itself, because A squared, it's a flip, so its inverse is a flip. Same with B, same with C. And D and F change the sense of rotation when you take the inverse. And then you start filling the rest. And I'll just fill it out. I did one calculation. You can check the rest of the table. So when you stare at this kind of tables and any problem that you do, pretty soon you realize they're so full of symmetries, you can just, you do very few multiplication and everybody else is just filled out by symmetries, by saying, anytime I have a reflection times rotation, I get this kind of thing, and every time I have rotation times reflection, I get this. I forgot D. And now, because of uniqueness, everybody has a unique inverse, etc. Each row is just a rearrangement of the original row. So each row has all elements rearranged in some way, and each column has them all rearranged. And in this particular case, because we are looking at the full permutation group of 3 elements, which has 6 operations total, 3 factorial, everybody is represented, so all possible reorderings are both in columns and in rows. A typical finite group is a subgroup permutation group. So have some, more specific structure, and this is very general. And now, what does this have to do with the regular representation? So I can write matrices in the following way. I can write a matrix D, index regular, of group element identity as a 6 by 6 matrix, which has 1s on the diagonal, 0s elsewhere. So that's kind of obvious. But notice that says every time I see E in multiplication table, I have unity, otherwise I have 0. Then I can write the regular of matrix A as I have 6 spots to fill out here. 6 spots to fill out in every row and column. And now whenever I see A in this table, I'll put 1. And because every row and column is just a rearrangement of the 6 elements, A shows up only once. So this is a matrix full of zeros with only 1 place. And now it's an exercise which I will not do on the blackboard, but it's an exercise that if I, for example, take 2 elements, so if I take matrix D regular of corresponding to group operation A, multiply from the left on the group operation of D, I will clearly get something that only has 1 per each column and row. Rest is 0, so it will belong to this group of matrices. And indeed, you can verify in particular case, and then you can prove it very simply in a general case, that this will obey our multiplication table. So that's why we call it a representation. It's a matrix representation, and it's called a regular representation because this is a representation constructed just from the abstract algebra of the group. So no matter what this group acts on how many dimensions, what other matrix representation has it, no matter how it acts on functions, etc. As an abstract group, it always has this set of matrices. But what is this set of matrices? A matrix that has only ones and zeros, we can always write as a Kronecker delta. So we can always write it as delta of matrix A in this particular case. And on the right-hand side, only ones that are allowed are the group elements. So if I call these guys, if I call them B minus 1, and I call these anybody from the row A, I'm only allowed to get the contribution from the combination. When I multiply A by the inverse, I get a group element. But that's exactly the representation we discovered when we were looking how the evolution operator works on the tiles. So that's why we care about regular representation. It's intrinsic to the group. It's totally, multiplication table is definition of the group. This is the natural representation for the group. Everybody else is just a special case of some other action of the group. And this is the one that we found in symmetry reduction of evolution law. In particular, it has an interesting property. So character of any matrix is defined simply as its trace. So psi of any matrix, it's called GI, is its trace of the matrix representation of the group element. But if this is a regular representation, then we find out that psi of identity is the number of elements in the group, order of the group. And psi of any other element, gi, is 0 if gi is not equal identity. I like it to be inverse because what this formula means is that geometrically, I go from fundamental domain. That's my reconstruction equation. It tells you whether I'm in big space. Then I use my evolution law, I land someplace. Then I go back into fundamental. That's why they're inverse. And the product of these two operations is the relative group shift from initial point any place to final point any place. And equivariance means that they're all physically equivalent if they have the same relative shift. That's why I like to write it this way.